Okay, so we're going to look at this particular situation where we're trying to span a particular vector space, in this case R2. And the most commonly used vectors to span R2 are, of course, what we call the standard basis vectors, 1, 0, and 0, 1, commonly called I and J. But the fact is that any set of two linearly independent vectors from R2 will span R2. So here we have set B prime made up of U1 prime vector called 1, 1 and U2 prime vector referred to as 2, 1. How can we get the coordinates of a vector relative to a different basis? Well, let's start by understanding what we mean by a coordinate for a vector from the standard basis. When we say the coordinate 7, 2, which I can refer to as a column vector 7, 2, we're going to call that vector v relative to the original basis b. We'll call that the old basis. And the reason why it's called 7, 2 and why that's so easy for us to grasp is because it simply means 7 of the I vectors plus 2 of the j vectors. 7 times 1 is 7, 7 times 0 is 0, 2 times 0 is 0, 2 times 1 is 2, and when you add that up, of course you're going to get 7, 2. But the question comes about, how can we obtain this vector? That is, how can we get to the same location using coordinates relative to a different basis, namely basis b prime? That is, how many of these vectors called u1 prime, how many of this vector, u2 prime, when put together, will get us to the same place? Well, with this type of scenario, it's 2 by 2. You could probably just think it through and do a little trial and error. And if you think about it long enough, you'll come up with the following. To get 7, 2, you simply take -3 of this new basis vector 1, 1, plus 5 of the second new basis vector 2, 1. Here's how that works out. -3 times u1 prime plus 5 times u2 prime would clearly be -3 plus 10, 5. And what does that give us when we add them together? Our old coordinate vector 7, 2. It's interesting though, this linear combination of the new basis vectors takes us to the same location as the linear combination of the old basis vectors, which gives us the coordinate 7, 2. So looking at this, we can get what's called a new coordinate relative to basis b prime. This new coordinate relative to basis b prime simply records the numbers that were needed as scalar multiples of the new basis vectors. Now, we did some guess and check, but is it possible to avoid guessing? And the answer is yes. You can use simply a linear system to represent what you're looking for. And you could represent that linear system by an augmented matrix. In particular, if you look at the basis vectors as the column vectors of a coefficient matrix, you're asking, well, what constants multiplied by these column vectors will give me the result 7, 2? And in creating that augmented matrix, you could easily take the reduced row echelon form, and lo and behold, out pops the new coordinates -3, 5. Now, we're guaranteed that this will always work because these new basis vectors are linearly independent. That's what enables them to be a basis for R2. They're independent of one another. So we know that when we take the RF of a linearly independent set of vectors like this in a square coefficient matrix, we're going to get the identity matrix and out pops our new coordinates. But another question comes up, how could we have achieved this same result of getting these new coordinates relative to a new basis by matrix multiplication? Well, the fact that this square coefficient matrix is invertible is logically equivalent to saying that it can be used, its inverse could be used as a pre-multiplier to get the same coordinates -3, 5. So for this coefficient matrix to be expressed in reduced row echelon form to get 1, 0, 0, 1, that's logically equivalent to saying it's invertible. Let's pre-multiply both sides by that inverse. So here's the linear system with coefficients next to the coefficient matrix, the variables rather, C1, C2 next to the coefficient matrix. And we find that if we pre-multiply both sides by the inverse, we will indeed get -3, 5. And in this case, the inverse of the coefficient matrix turns out to be -1, 2, 1, -1. And pre-multiplying on both sides gives us the new coordinates -3, 5. So is it possible to generalize this so we could use this process in every case? Well, the very process that we did here can always work in every case because we're guaranteed that the matrix whose columns are the new basis will be invertible since basis vectors, as we said, are linearly independent. So we have this little equation here which kind of sums up what we've done so far. We start with a vector relative to an old basis B. We want to find a matrix, we'll call it matrix P, that will transition us from that original vector to another vector relative to B prime. I should really say another expression of the same vector relative to basis B prime. So how do you get this transition matrix? And notice, please, the notation of this transition matrix. It's matrix P that takes us from the old basis B to the new basis B prime. That is, it will reveal the new coordinates relative to basis B prime by starting with the old coordinates relative to basis B, simply by multiplying on the left of that vector expressed relative to basis B. So the question is, how can we find that transition matrix P that goes from B to B prime? Well, since we've already stated it's invertible, we can use our row reduction techniques to reveal what that transition matrix actually is. So all we need to do is put the new basis, all the column vectors of the new basis, augment it right next to all the column vectors of the old basis, do our reduced row echelon form steps. Since we know the new basis is invertible, on the left of the augment line we'll have the identity matrix, but the beautiful thing is that on the right side, the transition from old to new will be revealed by a transition matrix on the right. So let's see what that looks like for the problem we just did. On the left of the augmentation line you see two columns. That comes from the two basis vectors that we had in the new basis B prime. To the right of the augmentation line we have our old basis vectors, 1, 0, 0, 1. When we perform the reduced row echelon form, as we suspected, we'll get the identity on the left and out pops the inverse on the right. In fact, this was a means of getting the inverse that no doubt you studied when you first learned about row operations. And you'll take that matrix, once you get that stage, you'll take that matrix, you'll pre-multiply it by the standard coordinates from the old basis, and out pops the coordinates relative to basis B prime. So once again, this is a standard procedure that will work when going from any old basis to a new basis. Simply augment, RF, and use your result as a multiplier to get your new coordinates.